So I want to thank the organizer for making the prettiest badges I've ever seen, and also for, of course, putting together this wonderful conference. The work I want to talk about was started in this paper that I wrote over the summer. Okay. I wrote over the summer with Miguel Correa. We were thinking about this wave regime and the structural resolution and stuff like that. And by complete chance, so at some point in spring, we heard a talk that Giulia gave at McGill about this GQ Raman scattering. And we didn't know much about log numbers at the time, but we quickly realized it was the same regime that we were also thinking about, and started wondering whether some of these ideas and understanding could actually be helpful in order to, on a technical level, to address this problem of matching log numbers. So this is work that I've been doing, of course, with Miguel, but also with Simon Caronwood and Michael Solon. The results are really fresh out of the oven and hopefully will appear soon. Let me also mention that both Michael and Miguel are here in case you want to chat more with us. And so we already heard a lot about classical limits. I wanted to give you just my picture. And I want to do this purely in kinematic point of view for a 2-to-2 scattering in the center of mass. So what are the scales? In kinematical scales, we have the IVA parameter of the scattering event, or if you want, the length scale probed by our experiment, the wavelength of the scattered wave packet, which if you have a massive state is the de Broglie wavelength, which is a scale associated with quantum mechanics, or if it's massless, it's just the wavelength of the wave. And then we have the Compton wavelength, which there's one associated with any particle in the spectrum, and it's really something that you can, like a scale associated with a vacuum, so something related to particle production. So if you probe a photon at the wavelength of at the length scale of the electron Compton wavelength, then you will probably see it split into electron-positron pairs. And those are really QFT effects that I want to get rid of, so when I talk about classical scattering, I'm always going to take B much larger. Once you impose this, there's a bunch of possibilities left. So let's see if you scatter in massive state and you take a B much larger than the Broglie and Compton wavelength, we are basically in the regime of classical mechanics, so point particle. So you can think of, like, I don't know, tennis balls. If B is of the order of the de Broglie wavelength, but much larger than the Compton wavelength, you have quantum mechanical effects. But this inequality also imposes, This inequality imposes also a non-relativistic limit. This is the simplest way to see if you want to do relativistic quantum mechanics, then you need particle production in QFT. If you scatter in massless states at very large impact parameter, then you are in the geometric optics limit. So you can think of some, I don't know, ray of light following a node geodesics next to a compact object, like light deflection. And on the other hand, when B is of the order of the wavelength, then it's some kind of spectroscopy experiment where the wave comes in and interacts and then it leaves, and you can tell something about the object you're scattering against. This inequality enforces a probe limit, which basically tells you that the black hole that you're scattering against will not back react. Okay, now many people here care about trying to describe waveforms, or like try to describe what we see in our detectors. And if you're interested in describing a spiral limit from an amplitude calculation, of course, you would go into this Econo regime. While if you care about the ring down, then you should probably work in the classical wave limit. At this point, I should probably say a lot of things and cite most of the people in this room, but let me instead just jump straight to the point that I want to make, which is the following. Something amazing we know about the spiral is that the amplitude exponentiates. And this is very cool because it exponentiates in like a large phase, so it's a highly oscillating object that then gives some saddle points. These saddle points are related to classical GR observables, and we know what's going on. This is also very technically helpful because if you Taylor expand an exponential, there's going to be pieces which are iterations, and so they don't really give you any information, and pieces that you actually care about, and this helps you to organize your calculation. Now, the question we ask ourselves is, okay, what is the most natural way to express our solution if you care about the ring-down phase or this wave regime? And our claim is that the most natural way to do that is through a Born series that here I wrote as a operator form. So B is going to be a potential and G a Green's function. Now, everything I'm going to say today will be focused on this classical wave regime, but the reason why we call it Born regime and not just classical wave is because this actually, it's a discussion that is valid also for a larger set of like physical phenomena, and this you can also use this for quantum mechanics. There's some fun story related to bound states and like energy levels and I don't know, decay rates of positronium, and there's a lot of cool stuff that you can do with this. But for today, let me just focus on this classical wave. Okay. So let me start by introducing what I mean by the Born regime, and let me do it in the space that most of us are familiar with, which is the scattering amplitude. Now, in momentum space, the condition of the Born regime translates to just a large mass limit, while the frequency of the wave is of the order of the exchange momentum. Okay, so the claim, as I said, is that in the Born regime, the amplitude naturally organizes itself as a Born series, something that looks diagrammatically like this, so iterations of a potential. And if you write this in some integral form, G is basically this Green's function. Okay, it's a retarded Green's function. So let me just like show you explicitly what this looks like for gravity. So if you want to describe a wave, a massless wave scattering against a black hole with like, let's say, Feynman diagram, the first diagram you would draw is this one. Let me take a scalar wave for the rest of the talk. And this is a simple tree-level diagram. It has a T-pole. And if you Fourier transform this to position space, you're going to get the Newtonian potential. Let's go to one loop. This is the type of diagram that contributes to this limit. If you take the contribution in the large mass limit of these two diagrams and you manipulate them a little bit, I will spare you the derivation, you can actually show that indeed it takes the form of this tree-level potential with the Green's function that I showed you earlier. Okay, what about the rest? The rest, if you compute this, you get two pieces. What are these two pieces? So to understand that, let me first take the Econo limit, which or like the post-Minkowskian limit that you may be more familiar with. How do we do it? Well, if we want to take the Econo regime, we're going to have to take a large frequency limit that brings us to the geometric optics approximation. If we do this, indeed, we're going to have one piece that dominates over the other. And you might have seen this before. This is precisely the correction to the deflection angle of light against a compact object, which you might have computed at some point in GR. This same diagram, by the way, if you do for the massive case and you're not familiar with the story, is what gives you the Mercury perihelium shift, okay? Okay, so this piece we understand. What about the next one? And to understand this, I want to introduce another side of this story, which is the wave equation. And here I have a slide which is basically a review from like textbook quantum mechanics. But let me still go through this. So let's say you have a wave equation with a given potential. Then the wave function at very large distances basically is given in terms of an incoming wave and an outgoing wave. And the way we define a scattering amplitude in quantum mechanics is just the amplitude is the coefficient of the outgoing wave. This is also a differential equation that you can solve in general with a Green's function, which, by the way, is the same Green's function I was showing you before in momentum space. And if you, in a few lines, put together these two pieces of information, you see that this amplitude has to satisfy a Liebman-Schwinger equation. And if you expand the Liebman-Schwinger equation at small potentials, you recover a Born series. So the fact that the Born series organizes itself, the fact that the amplitude organizes itself as a Born series shouldn't come as a surprise if there is an underlying wave equation. What is the underlying wave equation for this scattering process in gravity? Well, is the Reggie-Wheeler equation, which is nothing but a massless scalar wave, in this case scalar. So this is the equation of motion for a scalar on a Schwarzschild metric. And this can be rewritten indeed as a wave equation of this form, where V grav, here I wrote it in isotropic coordinate, is something that we know at all order in G and contains the horizon here. And if I expand this perturbatively in G Newton up to G squared, I'm going to get all these pieces. And indeed, if I Fourier transform the leading piece in G to momentum space, I recover the tree-level exchange. If I do it for the G squared, well, I have two pieces. The 15 is the one that survives in the Econo limit, and then I have an extra piece that indeed exactly matches the calculation that we did earlier. So the lesson to learn here is that if I have an underlying wave equation, the amplitude will literally be just a Born series of this iterating this potential. Okay, so there is an additional space that I need to mention before going further, which is partial waves. And the reason why we need to introduce this is because this, the Reggie-Miller equation is a hard differential equation. And as far as I know, the only way we have to solve it is to project this in spherical harmonics and separate into a radial and angular part. Most of the juicy stuff is in the radial one, and then you can get a solution. Solutions are either perturbative in this MST method, but since 2022 we also have a all-order solution, like an analytic solution, even in terms of vector superposition functions. Okay. So on the other hand, if you have the amplitude and you want to get partial waves, then what you have to do is just an integral over the momenta q against a Lejeune polynomial. Now, this is basically what we need to go further, but just for completeness, let me also mention that if you have a wave equation and you want to reach the Conner regime, then what you have to do is to take a WKB approximation, so replace your wave function with an exponential phase. And if you have your amplitude in partial waves, what you have to do is to take the large angular momentum limit, and what you end up, we will exponentiate into this radial action, so this classical action. Okay, so this is the picture we have in mind. There's an amplitude, which is a Born series, and then there's this full all-order GR solution that lives in partial wave space. And I guess we can call this the iconohedron. But okay, anyways. So let's say the discussion so far has been a one loop. So what happens if we keep going? At some point in this loop, calculation, and exactly when this happens will depend on what is the wave that you're scattering. At some point, you're going to get a UV divergence. But it's good that we know how to deal with UV divergences, so what we're going to do is introduce some counter terms, which in this case are basically just the four-point function contact terms. And these pieces, these log numbers, will have a 1 over epsilon piece that will cancel the UV divergence, and there's going to be a finite piece that we want to match to something, and what we want to match it to is the black hole perturbation theory. And this is precisely what was explained in Giulia's talk, and also Zian mentioned it, and what they did in this very nice paper, where they did the amplitude calculation at two loops, translated in partial waves, and match it to black hole perturbation theory, and that fixes your log numbers on shell. And this brings me to, okay, going fast, okay, to the second part of this talk, where it's basically like how we approach this problem of fixing the log numbers. Okay, so the approach we took is that instead of going from the amplitude straight to partial wave, we took the other way around and go through the wave equation. And what allows us to do this is the fact that we know that secretly in this regime the amplitude is just a Born series. It's secretly a Born series. So what we can do is just take in the Born series in let's say operator form, and then I can sandwich this with whatever states I like. And in particular, I can do this directly in partial waves. And so this is the general idea that we use. It's like we can compute this Born series directly in partial waves. Something that we found that was actually very useful is this book from 1972 by a certain Taylor, who actually worked out in detail the Born series in partial waves, and it was very helpful. Okay. So at this point, what we're proposing starts to look very much like the gravity calculation, the gravity side of the story. So let me put the two side by side and kind of highlight what the difference is. So on one side, we have the standard GR approach, and then on the right-hand side is our EFT calculation, which then we want to match to the left-hand side. So both cases have an underlying wave equation with different potentials. So what are these two potentials? In the GR calculation, it's going to be our all-order EG potential, which also includes the horizon, of course. While in our EFT, we basically expand the potential at perturbative EG. And as soon as we do that, we basically erase the horizon. So this is just like powers of 1 over r. In addition to this gravitational potential, we also have the effects from these love numbers. So these contact terms that I was showing you earlier, they are basically analytic functions in a Q, and if you Fourier transform an analytic function, it's going to give you a delta function, derivatives of delta function. So we can compute exactly what this V love looks like in terms of the word line that I showed you earlier. Okay, what about boundary conditions? So in GR, we know there's a horizon. This is a second-order differential equation. We can solve it and impose the ingoing boundary condition at the horizon, as is the case for this way of solving the Koski equation. So what are the boundary conditions that we naturally impose in QFT? So if you take the Feynman propagator and you go to a partial wave space and you look at how it behaves at r equals 0, you'll find that it vanishes. So every time we do in a QFT calculation, intrinsically we're actually imposing some like Dirichlet boundary condition at r equals 0, which is something that I personally never appreciated. But which is kind of crazy because we're imposing something in the UV just by using the propagators that standard QFT. Like we're imposing somewhere where we should have no business saying anything, right? Okay, and that's what the problem is, because basically we're imposing boundary condition at r equals 0 over and over again, with a potential that is more and more singular in 1 over r, and that's where at some point things blow up, and that's where UV divergences emerge. And so we need to somehow regulate these UV divergences. One way, which is the standard QFT way, which is also what we did, is to reg, so move away from 4 dimensions. And something that we observed in all this in those calculations is that what this really amounts to just to shift L, the angular momentum, with an epsilon factor. In principle, we could also just simply work at non-integer L. Also, if you have played with this black hole perturbation theory solution in 4 dimension, you actually see emerging all these 1 over L poles at integer L's, and this is precisely the UV divergences that I'm mentioning here. Okay, so the plan is the following. We have this EFT wave equation that we want to solve, and we're going to solve it using all these iterated Pauli integrals. And the way we're going to do this is basically do it in 2 regions, a small r and a large R. You can think of splitting these integrals from 0 to r and r to infinity. So let me show you how this is my only technical slides. Be patient. And I want to show you how this looks like if I turn off all the potentials, okay? Let me turn off, so this should be like a trivial case. So let's start from the small r regime. So if you solve the wave equation in d dimensions at small r, there are 2 solutions. There's a regular solution and a irregular solution. So the wave function is going to be some linear combination of these 2. If you go to large r, leading order solutions are given in terms of Henkel functions, which at large r basically becomes some ingoing and outgoing spherical wave. And once again, phi is going to be some linear combination of those. But those 2 are basically a solution of the same differential equation, so they 2 should match somehow at some point. And what you can write by imposing this condition is a relation between A1, A2 and B1, B2, which is basically given in terms of this matrix, which is some combination of like a Wronskians, basically. You can do this, and at this point, what is the S matrix? The S matrix is just the ratio of A2 and A1, and which looks like this geometric series. And then what we have to do is impose the QFT boundary condition that I was mentioning earlier, which is basically amounts to put B2 to 0. And once you do that, you find that S matrix equal to 1, as it should, because this is the trivial, no potential. Okay, now let me turn on VLOV. VLOV will contribute in this near zone. I'm going to start iterating it, this VLOV potential. I'm going to do it once, I'm going to do it twice, and it's 0. Basically truncates immediately the series. This is an exact solution. And in particular, it generates an irregular solution, okay? What I did is like set the boundary condition, throw it away, I turn on VLOV, and this turns on again the irregular solution. And this gives me a direct relation between this coefficient of the irregular solution and the love numbers that were entering my word line action, which looks something like this, where AL is some normalization. Okay, what about large R? Well, I told you earlier that all these log numbers are delta functions at r equals 0. And so if I'm integrating from r to infinity, I have no support there. So my solution is going to be exactly the same. So what happens with this matrix? Well, the matrix is going to be exactly the same as the one I showed you earlier. The only difference is now we have a below appearing in the irregular solution. And then again, I can compute the S matrix, which is this ratio, and it becomes basically a geometric series. And then I can expand in below, and I'm going to obtain the contact term, and then iteration of the contact term. You would get those diagrams if you compute these like bubble integrations in momentum space. And this allows us to basically get log numbers at all orders. This looks very much like a 1PI reservation, by the way, that we learned in QFT. Okay, now let me turn off below and turn on the graph. And again, we're going to do all these Born integrals iterations of the potential, the gravitational potential. And so in the small r region, these integrals are actually very simple, like r to the alpha. They can be done basically instantaneously. At large r, these are integrals, again, with like all these bezels and 1 over r's. And so those are a bit more complicated, but we were able to recast all these integrals in terms of HPLs. Which is something that, like Giulia mentioned on Monday, they had this suspicion they were all HPLs, and we can show that it's indeed all HPLs. And so we can basically compute this at any order. Now, this time, the matrix is going to become a function of G. And if we compute the ratio and expand it in G, this will generate all the diagrams, all the gravitational diagrams. Okay. Now, let me show you the full solution if I turn on both the potentials. So this is what it looks like. We're going to have a matrix. We contain all the corrections in G, the long-range dynamics, while all the log numbers will contribute to the boundary condition and the irregular solution. And again, we have this clear connection between below and the log numbers. Few comments. As I said, so this gives us a direct relation between the irregular solution and on-shell matrix, on-shell data, which I think is very interesting because the way the GR community has been defining log numbers is by taking the coefficient in front of the irregular solution. And this gives us a way to streamline basically the irregular solution all the way to on-shell data. You can fix it at a word line action, and then you can use this to go to waveforms in spiral problems, like the sky is the limit, and this is very nice. And basically, I think this tells us the GR community they've been doing things correctly all along. But what is really nice, because this definition is gauge dependent, while when you get this matrix, then it becomes gauge independent. Another comment is that if you want to do this calculation in momentum space, there's a lot of complicated combinatorics that comes in, all these like graviton exchanges and contribution from the log numbers. And but all this complicated structure is completely trivialized in this form, because basically it reappears only once you take the ratio of the A1 and A2 and then you expand. And this like generates this Born series, the geometric series that reproduces all the complicated structure. And what we're also observing is basically near-far factorization at all order of the solution, which all the near or like short distance effects appear in the vector, while all the long range appears in the matrix. Okay. The last 5 minutes, let me show you our results. So this is the phase shift at L equals 0, and I'm turning off the log numbers just to not crowd out the slide, but there we also have them. And the phase shift up to G cube, we match with the results from this paper. And since we're able now to automatize and go to higher G, we actually are able to get some prediction at G to the 4. This is G to the 5, and as I mentioned, those are all HPLs, and indeed you see that there's the appearance of all these zeta values with increasing transcendentality. So for example, G to the 5, you get a zeta 5, and nothing crazier appears. Okay. Oh, and also, for example, G to the 5, you get more and more, divergent UV divergences, so this one perhaps was squared. Okay, so the point I want to make is that this is completely automatized, so we can basically go to any orders in G. This is what G to the 7 looks like for the S matrix at L equals 0. This runs on Mathematica in about 10 minutes, and we haven't like really tried hard to optimize it in any way, but we have it. And this allows us to finally have the phase shift that we can then compare with black perturbation theory and match log numbers. So let me show you what this looks like. So for G2 and G cube, G squared and G cube, and L0 and L1, we exactly match the, I'm very happy that we match the results from this paper. And the fact that we're able to go higher allows us to actually fix log numbers. Here we did it to G to the 5. Something that maybe I should mention is that we also show that, which gives us also confidence that we're doing things correctly, that at L equal 2, we have the first static log number for L equal 2 at G to the 5, and indeed we find that this vanishes. Okay. Okay, let me conclude. So I hope I convinced you that in this wave regime, the right way, or the natural way of thinking about the amplitude is in terms of the Born series. And we saw how UV divergences are really a consequence of the wrong boundary condition that were imposed at R equals 0. These are not UV divergences that tell you you need quantum gravity or stuff like that. This is like really like intrinsic in the way we are doing QFT. We found this direct relation between the regular solution that it's turned on by the log number potential and the on-shell log numbers. We also saw this explicit factorization between the short distance and long range effects, and we saw this at all orders. This allows us to fix all the log numbers up to G to the 5, but as I said, in principle, there's no, we can go higher, sorry. And finally, let me mention a few future directions. So the motivation we have in mind when we go so high in powers of G is the fact that, as was mentioned earlier this week, the first static log number for a graviton wave appears only at G to the 5. And we have any hope to see or measure log numbers in a detector is going to be a gravitational wave, not the scalar wave that I'm showing you. And of course, I mean, we haven't had much time to think deeply about this. As I said, we just finished the scalar, but I'm cautiously optimistic we should be able to do this in a. We have the tools needed to attack this problem in a, shortish time frame. At some point early this week, my talk was advertised as a talk about Kerr. I'm sorry if that's what you were expecting. But let me just mention that in the paper I wrote with Miguel, we have some results for a massless scalar wave on a Kerr background using this idea that there is an underlying potential and we can reconstruct the amplitude by Fourier transform, and we're able to actually resound this at every order in spin. That said, Kerr is a weird beast from QFT. I still don't fully understand it. I think this idea of like iteration can actually be useful to understand it better. So maybe next time I have more to say. And another fun application that we're thinking about and discussing with Miguel and JP Gatica, who's a student at UCLA, and Anthony Hinderton, is some application of this Born regime in the context of strong field QED, lasers basically. There are a lot of things are strongly coupled, but it's basically a Born series once again. And we think that like this idea of organizing the diagram in this way maybe can help us, learn something about that as well. And I think that's all I wanted to say. So thank you very much.
So, any questions for Giulia?
Very cool, first of all. Second, I guess you couldn't talk about dissipation, but maybe you can make some comments.
Yeah, so yeah, I swept that completely under the rug because I didn't want to make this heavier. But yeah, we basically do it with the sugar Geldish, basically what you presented on Monday. But they enter in the same way. Like this B love, which is given as sum of CL, this will include also the imaginary pieces that enter there. Like basically BL is your 2-point function.
Okay. First of all, thanks for the excellent talk. Regarding the strong field QED part, how easy would it do you think it would be to translate all you've done into the language of strong QED? Do you think it'd be an easy translation, or do you think there'd be additional challenges?
So as far as with, I mean, this is like really like very, very at the start. But as far as we can see, there's like an additional complication of like having like you scatter basically coherent states, so you're gonna have higher legs appearing. But it looks like we can also organize this in a simple way, and yeah, I don't know yet. I will let you know.
Thank you.
Thanks for an interesting talk. So just a tangential question to what Julio mentioned. Are you including like horizon effects as delta functions, absorption effects? Because
Yes.
because I only saw the love numbers.
Yeah. I know. As I said, I was a bit. I didn't want to make this heavy, but like basically this sum here contains also odd powers of omega.
Okay.
So
Thanks.
if you do this, yeah.
Questions for Giulia, Kevin?
Can you just comment a little bit about how the vanishing of the static love numbers comes out of the calculation? Is this like a trivial observation, or do you have to do a detailed calculation to see it, or these discussions about symmetries that lead to the canceling of the love numbers?
I don't know why it's true. In terms of like checking it, then we just get our EFT output, and then we match it to black hole perturbation theory, and it's the same. Therefore, the love number is zero. Like a very, it's by comparison. Like you ask me why zero? Like
Okay,
what's
so
the deep reason why?
Does it give you any additional insight into why they're zero?
Sorry?
Does it give you any new insight into why these are vanishing?
You know. So maybe something I can mention here is that if you go to G to the 4, then you start having actually iteration of log numbers themselves that you have to take into account. Because the first log number is a G squared, so if you go to G to 4, you're going to also have those. And you also have to take this into account when you do the matching, which is the kind of things that I want to mention.
Maybe I'll also ask, so if you go to higher orders, is the bottleneck in the EFT side or in the black hole perturbation series side? If you go to even higher orders, do either side you can just in principle keep going on forever, or there's some bottleneck?
There's no, I mean, my laptop is not like my ability to write a book. But yeah, no, there's no, you can go to any G.
Any other questions? Okay, if not, let's thank both speaker again.